Hello and welcome to Mr. Linford's Math 097 course. This is a presentation on section 4.1 and section 4.2 of the text. This is the beginning of what we're going to call Unit 5, Systems of Equations. And in today's lecture, we're going to be talking about what is a system of equations. We're going to look at it graphically, look at what it implies for the solution when we have a collection of equations, as well as we're going to look at a method for solving them called the substitution method. Now, beginning with this text, we're going to talk about just what is a system of equations. So for us, a system of equations is going to be a collection of equations in same variables. Terrible handwriting. All right, so a collection of equations in the same variables. It's important to remember that when we have a system of equations, we have things like 2x plus 4y equaling 3 and 3x minus 5y equals 7. There, we have a collection of equations. In fact, I got two equations, and they're in the same variable. They have the same x's and the same y's. That's important. We don't want to have something like a system like this and then throw in 4z plus 5k, let's say. I don't want to throw that in because they're different variables. They're not the same thing. We need to have them be the same thing. They need to be of the same variable. And the reason for that is because we're going to want them to be the exact same numbers. So x and y in these two problems are exactly the same. Let me get rid of this right here. But in the system right here, x and y, the variables that we pick, they're going to be the same thing. They're going to represent the same value. So what we're going to want to do is we're going to want to figure out basically what x and y solves the system. Now, a solution for a system, when we say we're going to solve the system, let's pretend like we have a graph right here. Here's some graph, x-axis and y-axis. And I have an equation. Let's say this is my red equation. And then let's say I also throw in here some blue equation. Okay, two separate equations, and this forms a system, because that's really what a system is. Multiple equations of the same variable. So I was able to graph both of them, and they're both in terms of x and y. The solution for the system is the ordered pair that is a solution for one of the equations and the other. Now remember what it means to be a graph. We said that the graph of a line is really all the points on the line. The graph of the line is all the solutions of the equation. So the graph of the line, every single point you find on this blue line is a solution to whatever the equation is. And every point you find on the red line is a solution to the red equation. So if I came up with some equation for the red line, any point on that red line, I could plug that in and I would get a true statement. Same thing for the blue. If I took this blue line, any point on that blue line, and I plugged it in to the blue equation, I would get a true statement. So what we want to do is we want to find the point that is essentially a solution for both of them. I want to find the ordered pair that if I plug it in to the red equation and the blue equation, it works for both. That means I want to find the point where the two lines intersect. I want to find that single point right there. So we have to find a way of doing that. Now, there is the graphical method that I just showed you, where we just take our graph and we plot the two lines, and what we're going to do is look at where do they intersect. So I got some line here, and what do you know? There's the intersection, there's the solution. So the graphical technique, find the intersection. But do you really want to have to graph lines all the time? What happens when the intersection doesn't occur at a whole number, right? So like we've seen this situation before where the two lines intersect and they're kind of in between the spaces on grid paper. So you kind of have to guess, is it like 0.5? Is it 0.75? Like, is it 0.4? And we want to be pretty accurate with our work. So this graphical method, it's easy to see, easy to understand, but not the best to execute, right? Not the best to actually put together. So what we want to have is we want to have a purely algebraic method for doing this. And one of the methods we actually have a few, is called the substitution method. I'm going to do some work first, and then I'm going to go over what the procedure is for this. So here is our system. We have a system of equations right here, 2 equations. They're of the same variables. So what I'm going to do is I'm going to, for step 1, I'm going to pick one of these equations, and I'm going to solve for one of the variables. Well, I don't know, let's start with this equation right here. X minus 2y equals 12. And I'm going to solve for one of the variables. Why don't I solve for x? That looks pretty easy. So I'm going to add 2y to both sides. And we're going to get x equals 2y plus 12. Okay, so we just solved one of the equations for one of the variables. It doesn't matter which one. I just picked the bottom one because it looked easy to solve for x. Okay, what I'm now going to do, I'm going to take my other equation. I'm going to label this one the blue equation, this top one here. I'm going to take this other equation, this blue equation, and it says 3x plus y equals 8. Well, instead of writing 3 times x, I know what x equals. X is 2y plus 12. I just solved that from the previous equation. And what I'm doing, like the name suggests, I'm just substituting the value in. So instead of saying 3 times x, I'm writing what x equals. I already solved it. This x and this x are the exact same. These x's are the same. These y's are the same. We're finding what numbers are identical in x and y so that I can plug them in and it works for both equations. That's why I'm able to do this. It's super helpful and super easy. So what we're going to do now is we're actually going to go ahead and solve this. We're going to solve this, and notice how the benefit to this is I only have one variable. I have 2 y's here. I can solve this just like normal. So this is step 2, we'll call it. I'm going to distribute this 3 through. We get 6y plus 36 plus y equals 8. All right, let's see what we get here. 6y and y is 7y plus 36 equals 8. If I subtract 36 from both sides, we should get 7y equals negative 28. That's a terrible equal sign. Negative 28. So y should be negative 4. There, we just got an answer. We got y is going to be negative 4. Okay, but careful. I want to know what the ordered pair is. I want to know what x and y are. So part of my answer has been solved. We figured out that the y value has to be negative 4. Okay, so that part's set. But now what we have to do is we actually have to go and figure out what x is. Well, that's actually pretty easy, because look, you have 2 equations right here. You have one equation and the other. You already know what y is, so just plug it in. And in fact, I might even just use this equation, since they're the exact same. So, okay, x equals 2, and instead of writing y, I'm going to write what y equals, negative 4 plus 12. So x equals, let's see, that's a negative 8 plus 12. X should be 4. Yeah, that sounds about right. So my answer's been solved for. I just figured out what x has to be, and I figured out what y has to be. My answer is 4, negative 4. This right here is the solution to the system, 4 and negative 4. The big idea here is that in this process, my ultimate goal is to get to right here. I want to write an equation that just has one variable in it. If I had 2 variables, I can't solve that. I need to get it to one variable. So the first step is pick an equation and solve for a variable. It doesn't matter which equation you pick. It doesn't matter which variable you pick to solve for. I just happened to pick the second equation. I said, I'll solve it for x. I could have solved it for y. I could have picked the first equation and solved it for y or x. It doesn't matter. However, once you pick, you have to substitute. You have to substitute that value. Really, it's an expression. So you have to substitute what you get into the other equation, EQS, I'll abbreviate. Sorry, my stylist writing isn't any better. You know, I keep saying that, but really my handwriting is just pretty bad in general. But this is the idea. You pick an equation, and then you solve for one of the variables. That's what we did here in step 1. But then, once you do that, you got to substitute it into the other equation. That's very important. It's got to be substituted into the other equation, the other one you didn't use. Once it's substituted in, solve it like normal. That's the last step here. Solve it like normal. Okay. Let's practice this idea. So we have some practice problems right here, and I'll write down the answers to them, but let's go ahead and actually try to, use some of this technique. In this first problem, we have to first pick an equation and get a variable solved for. Well, doesn't it look pretty obvious? We already have one solved for. So let's just use that. So we have an equation with a variable already solved for. So I'm going to take 4x plus 12y, and I'm going to substitute in 5x plus 11. I'm going to substitute that in for y, because this equation says that's what y equals. So I'm going to substitute it in. So we end up with 4x plus 60x plus, is that, let's see, 12 times 11 should be 132, and that will equal 4. All right, let's do some combining of like terms. This side is going to have 64x on it, and if I take 4 and I subtract 132 from it, that should be negative 128. So if I do some division, x will equal, that should be negative 2. Yeah, that'll be negative 2. So x is negative 2. Then, I'll change colors here. To figure out what y is, just sub in negative 2 for either of these equations. I'll do the bottom one because that looks easier, and sometimes we get kind of lazy with these, just because they can get a little tedious after a while. So just try and, pick the easiest equation you can, but it doesn't really matter. So when I sub in negative 2 for x, I get negative 10 plus 11, which equals 1. So y equals 1, x is 2. So my answer is going to be negative 2 and 1. It's the ordered pair. I need to know what x and y are. So there we go. Let's try another problem, but this time let's try one where we got to do a little more work. That one wasn't too bad. In fact, let's try something like number 2 here. Let's try number 2. We got to pick one of the equations, got to solve it for a variable, got to sub something in. So, I don't know, looks like the first equation might be pretty easy to solve. I'm going to take the first equation, and I'm going to solve it for y. So let me add the 2y over, so 12x equals 2y. I'll divide both sides by 2, so 6x equals y. Okay, that's pretty easy. Now, let me try changing colors here. Actually, let me go to green. And what I'm going to do is I'm going to sub in what y equals for the other equation. So 7x plus, instead of y, I'm going to write 6x equals 1. So negative 7x plus 6x equals 1. I have it now where I have one equation of one variable. This can be solved very easily. So let's see, that's negative x equals 1, so x equals negative 1. Yeah, barely any work right there. That's super easy. And then if I want to figure out what y is, I can just sub it back in. I could sub x into one of the original equations, but you could also plug it into this one. I'm probably going to plug it into the second one just because it's easier. So y equals 6 times negative 1, which is negative 6. So my answer for this problem is negative 1 for x and negative 6 for y. that's kind of messy. And in this way, I'm figuring out graphically where these two lines are going to intersect. But really, I'm just doing it algebraically. So this system isn't too bad. Give it some practice. See how it goes for you. I'm going to put on later on another technique that some students tend to prefer to substitution. Some students like substitution. Some students like this other method. And in fact, I have another method that can be even easier to solve these systems. Now, if we're going to move on, let's talk about some weird systems. Now, sometimes systems don't always behave like we want to. Sometimes a system can have one unique solution. So if I have a graph, let's say got a couple of different graphs here, and the nice easy answer is when they have two solutions. You have one line, you got another line, and they intersect. They intersect one time, and you can find that pretty easily. But sometimes there could be no solution. Why don't you pause the video for a minute and try and think to yourself, what does it mean for there to be no solution? How could a system of equations not have a solution? Remember, here's a hint. A solution is where the two lines intersect. So pause the video and take a minute to think, what could no solution look like in a system? All right, well, hopefully you had time to think about it. But when it comes to no solution, that key idea here is that there's no intersection. That means I got one line right here, and then I have the other line running parallel to it. That means that these two lines being parallel are not going to intersect at all. So if they don't intersect, there's really no solution. There's no coordinate point or ordered pair that I could plug into both of the equations to make it true. Now, another really kind of weird situation is where I have infinitely many solutions. Try to take some time to think about what would it mean to have infinitely many solutions. Well, a solution is where the two lines intersect. So I have infinitely many intersections? What would that look like? Okay, we're just talking about what would infinitely many intersections look like, because that's what it means to be a solution. It means to be an intersection. So if I have infinitely many solutions, I have infinitely many intersections. So I'm going to try to draw this as best I can. Let's pretend we had some line there, some red line. And then I'm going to take another line, the blue line, and I'm going to draw it right on top. This is where one line is on top of the other. One line on top of the other. And what this is saying is you basically have the exact same line. You have two of the same line. And the equations might look different. One might be a multiple of the other. But end of the day, if you solved it for y equals mx plus b, let's say, you would have the exact same line. And so the same line intersects with itself infinitely many times. That's how you can get infinitely many solutions. Now, these systems have different vocabulary to them. There's something called consistent and inconsistent, and then there's something called dependent versus independent. A consistent system has a solution. An inconsistent system has no solution. Okay, so consistency, whether it's consistent or inconsistent, that just talks about if it has a solution or not. A dependent system and an independent system talks about how the equations are related. An independent system basically is different equations. But a dependent system is basically the same equation. They're the same. So in this problem down here, let's go ahead, I'm going to use purple, and let's try and label some of these. So for this first one, the one unique solution, this is consistent because it has a solution, and it is going to be independent. I'll abbreviate that. It's going to be independent because clearly the lines are different. Now, when there's a no solution, this is going to be inconsistent, because there's no solution, but it's going to be independent because the two lines are different. They're not the same line. Now, for something that has infinitely many solutions, well, it'll be consistent because it has a solution. In fact, it has infinitely many, but it's also going to be dependent because it's two of the exact same line. And that's kind of the key idea here. And so sometimes you will see in the practice, and they're labeled in the practice and on the homework, where the two equations of the system basically give you an answer that is a dependent solution, or it gives you an inconsistent answer. And you'll see those cases, and we'll do some practice of those later on. But this is the general idea to what is a system of equations and how it might have different answers, and an idea of how to symbolically go about solving this. So that concludes this part of the video. If you have any questions, comments, or concerns, feel free to contact me. My email is Linford, that's Linford, at wccnet.edu. Feel free to send me an email. Let me know what you think of the video. And until next time, take care.